What's up, people? This is Coding Cleverly, and today we're going to be talking about the quicksort algorithm. So we're going to discuss everything. We're going to get the overview of what the quicksort is. We're going to talk about how it works. We're going to write the code, and then after that, we're going to do a review of the quicksort algorithm. Unlike the approach in merge sort, where we created new arrays at each division, we will do all of the sorting in place, meaning we are going to refer to subarrays by starting and ending indices of the original array. This saves a lot of space. Now, we're going to go first to the partitioning process, and then we're going to go to the recursive process. So merge sort, you're going to see the two things, and we're going to start and jump into the partition process first. Partitioning is the meat of the quicksort algorithm. It's here that we compare the elements and swap them. We will write this as its own partition method that takes the original array, a left pointer index, and a right pointer index. In the first call to partition, left pointer will be 0 and right pointer will be the array's length minus 1. Like I said, we have the left pointer index and the right pointer index. So what we will do is that we will use L to indicate where the left pointer is and R to indicate where the right pointer is. And then we'll also have P, and that would be to indicate the pivot element, which is the value of the middle element at the middle of the partition. Now the pivot could be anywhere. Now there's going to be so many implementations out there. Some people prefer to add the pivot in the beginning. You could add the pivot as the last element as well, the index of the last element, or you could also add the pivot somewhere in the middle. So this is like 1, 2, 3, 4, 5, 6. Since it's 6, we actually divide it with their index. So we could say 0 plus 5. With 2, we get the integer division here. So we get 2.5, so we get the 2, and this is 0, 1, 2. So, and other cases, people prefer to add the pivot in the middle, and so in this implementation, I'm going to prefer to add the pivot here in the middle. So the left pointer index is pointed here, the right pointer index is pointed here, and the pivot is going to be here. So we just say P as for the pivot. Now the first step is we're going to compare L with the pivot element. So 39 with the pivot element 24. As long as L is less than the pivot, meaning that it is on the correct side of the pivot, we want to move L forward one step to the right, plus 1. Here, L does not increment because it is greater than the pivot. This will be the element involved in the first swap. Since we have 39, which is greater than 24, which is our pivot, we're going to have to do some swapping here. So now that we're done with the left index here, now we go to the right pointer index. So L stays here, and now let's go to the right pointer index. Now let's do the same with R and the pivot. We are moving R to the left as long as the current element is greater than the pivot element. So here we have something 19 and the pivot element is 24. It had to be greater, so this is also contradicting. R also stays the same since 19 is less than 24. Both L and R pointers are paused. Here we have this one and this one paused, ready for the elements to be swapped. We should swap the elements at L and R. The pivot element's position can be swapped with another element, but the pivot value will stay the same. Just an exceptional case here. Now we have to swap it, so we use our swapping method. So I'm just gonna right now just write over it. So this is gonna be 19. And this should be the number 39. The while loop should start again. L increments while the element is less than the pivot. R decrements while the element is greater than the pivot. So you could see over here in the next portion, it's just going to increment plus 1. L is going to be here. So now we check if 19 is smaller than the pivot. And 19 is, and 24 is greater. So we're just going to increment here. We're going to go to the 15. This number is smaller than the pivot. And if it is, we're going to increment the left pointer index. And now it's going to point to the pivot. Now, we're going to go and check the right pointer index, and we can see that this is not 39, and since it's greater than the pivot 24, we're going to decrement, and we're going to go here, and we're going to check if 76 is greater than the pivot. Yes, it is. We're going to decrement again. 35 is greater than the pivot. Yes, it is. Decrement again. Now we're going to point to the pivot again. So both of these are pointing to the pivot, and the pivot itself is pointing to pivot. The pointers are paused here, this portion here. So if the left index, which is here, is equal to the right index, it is, the while loop ends, we return the left index L as the partition point. So we're going to return this thing as the partition point. Note that the partition point returned will only sometimes equal the index of the pivot element. In this case, it did return it, but in some cases, it might not return it. So I just got lucky here and got my partition point as the same as my pivot. But in other implementations or other ways or other cases, you'll have the partition point somewhere else as well. It doesn't have to be in the same pivot area. Create a method here, public, and let's create it as int partition. And we're gonna get the input parameter as the array, ARR. We're also gonna get the left pointer index, and this is just gonna be the index here, so we're just gonna say left pointer. And we're gonna get the right pointer, and we just add it as right pointer. First of all, we're gonna add in our pivot, PI, and we could just get the division of the two things, the left pointer and the right pointer, and then we divide it with 2. So we could say something like math.floordiv, integer division. So we could say math.floordiv. We got the left pointer plus right pointer, and then we divide it with 2. Add this up. So in the array, we want the value of the pivot. So we say array sub of this, and this would just give us the value. Cool. Now that we got our value here, let's do the next step, and that's the while loop. And the while loop is left pointer is less than the right pointer. So while left pointer is less than the right pointer, we want to do the things here. So the while loop, there's another while loop inner here, and I said there's a condition that we have to check, and we have to check if the left pointer is less than its pivot, right? If the left pointer's value is less than its pivot, then we just keep incrementing the left pointer. And in the other cases, if the right pointer is greater than the pivot, we keep decrementing the right pointer. Now a condition here is if the left pointer is less than the right pointer, just like the one on the top. This is where for swapping, in cases they're contradicting. So we use the swap.swap method, and you might be asking, where's the swap coming from? So I have it added here. So in the same directory, I have the swap method that we've previously created for our bubble sort method. So we're just going back here, and we're using the swap method, which is taking 3 inputs. Once the array, the index 1 and the index 2. So we're just going to pass in the array here. We're going to pass in the left pointer, which is the one, and the right pointer. There you go. And remember, this is an in-place swap, meaning it's doing it inside of its own array. It's not creating some extra subarrays or whatever. We're not wasting memory. Okay, after this, we are done, and if we are done with this while loop, we should have something that is fully partitioned, like we saw over here in our diagram. So once we have something like that, we actually return the left pointer. And why am I returning this left pointer? And this is because I use this as my partition point, and this is going to be known as my partition point. So I'm going to add something line over here so that we could remember here, returning our partition point. Cool. So now we're done with this. So this is our method here, which is the partition method, and it's going till here. Now let's go and discover the other part of this algorithm. Now that we've taken care of the part of the algorithm that rearranges elements and calculates a partition point, we need to structure the divide and conquer recursive part around that. First, we'll set up the quicksort method to take in the whole array, the start index of the current subarray and the end index of the current subarray. We do this instead of creating placeholder arrays for all of the partition subarrays. We're not using placeholder subarrays because that's going to cost us memory. We're not doing the same thing as merge sort. We're doing something different. Here we're going to use in-place methods. We're going to use our own array and just manipulate it, right? Like all recursive methods, we need to establish a base case and a recursive step. The base case is straightforward for sorting algorithms. If the length of the input array is less than or equal to 1, we should just return the array. The recursive step should execute if the input array length is greater than or equal to 1, or if end is greater than start. So now over here you can see that, like I said, end is going to be over here, and then there's going to be a start as well over here. So this is not going to be applying for just only this array. This is also going to be applying for all of those subarrays that are going to be broken out from this. And remember, I said we're using in place, so nothing's going to be affected. We're not going to create any new subarrays. It's just going to be affected here. So if end is greater than the start, this is the condition. For this condition, we need to add a recursive process. So that recursive process is going to go again and again and again, right? Until we end up in a base case or something. Now recall that partition method that we created earlier, this one. What it did return was a left pointer. And this is the partition point, like I said. And this is going to be the index, right? It's going to return us an index. You can see over here it's returning an int. In this case, if we look at this example here, 19, 15, 24, 35, 76, and 39, the partition point that was returned from that method was index 2, which is 24. Index 2 because it's 0, 1, and then 2. So over here, this one. That means the array can then be divided into a left partition of the array from index 0 to 2. And now this is important. You have to know that it's 0 up to 2. So it's going to be 0, 1, and 2. 2 is inclusive here, including the partition point. And then right partition of the array from index 3 up to the end. So we have this one, 3, 4, and 5. This is going to be for our right subarray. So right partition, this is going to be for our right partition, and this is going to be for our left partition, this portion here. Because of my recursive process, just created 2 new subarrays. So we're going to have a left partition, we're also going to have a right partition, and each of these have their own start. So the start will be over here, the end will be here. So we have an end here, so somewhere here, and then we have the end over here, and we also have a start over here somewhere. So this is going to create this partition, and then you're just going to recursively iterate through this again and again until we have one element or less than that in the subarray or in the partition array. Now we're actually left with 2 subarrays. So these 2 parts of the original array should be quick sorted recursively, and only if the lengths of each are greater than 1. We should enter in the correct indices of the original array as arguments for the recursive calls on quicksorts. Now that we've taken care of the part of the algorithm that rearranges elements and calculates a partition point, we need to structure the divide and conquer recursive part. So on top of the quicksort, we're going to create a method here. We're going to say public, and we're going to say int array quicksort. And we're going to pass in an unsorted array. So what's happening here is that it's going to check if the array length is less than or equal to 1. If the array dot length is less than or equal to 1, now we're going to have to suppose that if we are given an array with only one element that is already sorted. So one element array is by default sorted. And if it's less, then you're just going to have to return, right? So we're just going to return the array. There you go. Else case is that we have to return a call to a quicksort. And this is not the same method. It's going to be a different method. It's going to pass in the array. It's going to get the 0th index. And we're going to get the length of it. So we're going to say array.length -1. And this is going to give us the last index. And we're actually going to call a new method here. So it's going to be public, and we have array ints. We're going to call it as quicksort, and we're going to get the array that was passed in. So, and then we have the index, start index. We call this as the start. We have the end index as well, and we call it as the end. Awesome. Now over here, we're going to add in the conditional recursive logic that we needed for our quicksort algorithm. So let me just zoom this in, and then let's focus in on this method here. Okay, so the second one over here, second method, and we're gonna say quicksort. Now this is the actual code for this. So if end is greater than the start, we're gonna do that recursive process here. And first we're gonna get the partition, and how we're gonna get this is that we're gonna call our partition method that's over here on the bottom. It's asking for an array, the left pointer and the right pointer, right? So my pointers are gonna be the start and the end for now. So start and the end one, which is end. Okay, so since I got my start and end pointers, I could now do my other process here. But before that, I want to just show you that these left and right are now referred to as start and end. So I just wanted to add here, remember that I said the left and right during the partition place? The start and end are referring to those. See this start and end over here? And these are actually getting the 0 and -1, which are acting like our left and right. And then after that, we have start and end over here as well, which is the things that were passed in. But if we look at the partition here, partition is actually having the left pointer and the right pointer. And these are actually, and these are just imitating and behaving the same way as our left and right. So we can alternatively call our start as our left pointer and end as our right pointer. Just another name for it. So don't confuse yourself with left and right as being the same things. So we could just call them as start and end now, for now. And then when we're talking about the partition place, we're just gonna call them as left or right. So over here we have the partition. Now we're gonna add in the conditional. So I'm gonna say if the start is less than the partition, so what we're gonna do is we're gonna say quick sort recursively on the array. Now we're gonna start with the start right now, and we're gonna go all the way to the partition. Remember, like I said, it's gonna go up to it and inclusively. So this is how it's gonna work here. And in case if the partition plus 1, because we're not including the partition, but the partition plus 1 is less than the end. So what we're gonna do here is we're gonna call the quicksort again recursively, pass in the same array, and we're gonna go with the partition plus 1, and we're gonna go to the end inclusively. This will just end up with one element on each partition. Now after that, once we have those, we could just return the array, because we could know for sure that the swapping did everything for us and it sorted our whole array. So that we're just going to return that array. So now once it's done, we have that as a return type for this quicksort, and that's our value. So over here we could just pass in that. So let's create some instances here. So first of all, I'm going to create the quicksort object. So I'm going to say quicksort. I'm going to call it as QS, and I'm going to call this as new quicksort. After this, we're going to get an unsorted array. So let's say unsorted, and we're going to give some numbers. So let's imitate the one that we've created in our diagram, and that was 39, 15. And now we're going to just do a system out. So system.out.println, and we say sorting the array, and here we're gonna have the plus, and we're gonna use the arrays.toString method that converts this array to a string. So arrays.toString, we're gonna pass in the unsorted array, and then we're just gonna put a semicolon at the end. Awesome. qs.quicksort. Now we have two methods. We have one and second one. We're using the first one and just gonna pass in the array, and it's just gonna call the second one for us. And once it's done, so we actually didn't need to pass in array, but we need to pass in the unsorted. And what's it gonna do is it's gonna quicksort apply it for us. Since this is an in-place algorithm, the effect you will be seeing on the same array. So you'll have the QS modified. The array unsorted will be modified, and we'll just paste it here. But in this case, we'll say after sorting. One other thing that I want to just bring up here is that arrays.toString, I have it imported on the top. So there you go. Import java.util.arrays.toString. Okay, so this is my quicksort method. This is what's so I'm calling some quicksort method and I'm passing an array. So it's actually calling this one. It has this, and so its length is actually greater than, so it's going to call this method, and then after that it's going to call this one. And since partition is being called, so partition will be called here, and recursion will be applied here. So quicksort will call again and again, depending on which case it is, if it's left partition or right partition. And then after that we have the return array, and then we have this whole array sorted once it's returned. So this will give us the sorted array, and this will return it here as well. So we'll have quicksort return us a sorted array at the end. Right, so here I just want to add one thing. Here we have quicksort and we have end is greater than start. We have the partition, right? We got the partition. We're doing the recursion process here. So I'm going to say recurse on left partition here. And this one is actually recursion. So recurse on right partition. So this one is doing recursion on the left one, and this one's on right one. So we're just going to end up with a good array, fully sorted, and that will be returned here. Awesome. So let's run this code. So we're going to say quicksort.java. After that, we're going to say java quicksort. Now my array should be fully sorted. So after sorting the array, this one, after sorting 15, 19, 24. Awesome. 15, 19, 24, 35, 39, 76. Quicksort can be a tricky sorting algorithm, and there could be many variations to this. So let's look at the performance of the quicksort algorithm. Quicksort is an unusual algorithm in that the worst case runtime is O of n squared, but the average case is O of n of log of n. We typically only discuss the worst case when talking about an algorithm's runtime, but for quicksort, it's so uncommon that we generally refer it to as O of n of log of n. So there you have it. That's the video. Thank you so much for watching. Subscribe to the channel. Like always, I'll see you in the next one.